Ya, Assalamualaikum warahmatullahi wabarakatuh. And
Salam warahmatullah.
very good afternoon. Uh, I think we are going to start the webinar soon. To the presenter, please make sure you are ready with the slide. I think we will start in a few minutes. Okay. Okay, Alhamdulillah. Alhamdulillah. Uh, Thank you to the all attendee, to all audience who managed to allocate their busy time, join our webinar this afternoon. It is an honor to us. For your information, this is the second webinar that have been organized by the Metal Forming Research Lab. I would like to introduce the Metal Forming Research Lab at PPKM USM. We will start in 2006, where we just focusing on the metal forming process and also the coal forging process. And now we start to explore new direction based on the current demand. We still new in teller welded blank, which is I think less than 6 years. Still many things we have to learn from the others, especially the precision stir welding, laser welding, additive manufacturing, and the welded blank communities within Malaysia and outside of Malaysia. Now, for the research in teller welded blank, our main focus is on the post-forming evaluation. It is an honor today where we have two presenters to share their research. First presenter is Mr. Muhammad Fadzil bin Jamaluddin. His topic is low power laser welding of dissimilar aluminium alloy for lightweight application. Whereas the second presenter is Muhammad Zulkhairi bin Rizlan. His title is on formability study of aluminium steel friction stir welded blank. Without further delay, I would like to call first presenter, Mr. Muhammad Fadzil. And please note that Q&A session will be allowed after the second presenter completed his presentation. With then, please, Mr. Muhammad Fadzil.
Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Just want to check, can you hear me? Yeah?
Yeah, clear.
Okay, clear. Okay. Thank you. I will just share my slide. Screen. Okay. Thank you very much to Associate Professor Dr. Ahmad Bahrudin for the introduction. This afternoon, I will be presenting the updates of my research on the low power laser welding for dissimilar aluminum alloys, which is being used for lightweight applications. And team members, myself, actually, student here, and we have my supervisors, Dr. Ahmad Bahrudin and Zahurin, and Associate Professor Fadzil from University Malaya. Okay. The motivation for this study is based on the situation now where we are having a global environmental problems from the transportation. And because the transportation is a major use of energy, and as we know that the output from our combustion engines, so all are air pollutions and carbon dioxide, and this problem it's becoming worse because there are many developing countries such as from China and India where the status of life they are increasing and they are demanding luxuries, having cars on the road. Even though that we are having electrification in terms of electric vehicles and hybrid, from the source from the data, it is predicted that the vehicle will be keep increasing years by years. Even though maybe in the future the internal combustion engine vehicle are reducing, but the numbers overall it will be increasing, approaching to 100 million vehicles per year. So the concept of lightweighting, it is the concept of making the vehicle lighter, making the vehicle lighter regardless of the engine, whether it is using petrol or using batteries. So the concept is by building vehicles that are less heavy to achieve better fuel efficiency, while at the same time maintaining safety and comfort. And then because of this reason, there is a renewed interest and focus on lightweighting. And it is said from the literature that a decrease in 10% weight, it will translate to 5 to 8% increase in efficiency. So the key driver here is the carbon dioxide emission, and the manufacturers are investing in solution to solve this problem. The recent ones from the Hyundai, they have a technology lightweight development, just the recent 2019. They have a special unit on purposely on reduction of weight. And to reduce the weight, it is not just a matter of just replacing one material to another. It can also be in the form of redesigning of components, and also on the using of selection of the manufacturing processes. So with that background, just an outline of presentation today, I will be presenting an introduction on the tailor-welded blanks. It's not exactly a new technology, but we are seeing it being increasingly used in the automotive industry, especially for alternative materials. And as a topic on the laser welding, this is the welding. Steel is not something new, but new technologies in laser, which been having some interesting applications. And a little bit of my work on the experimentation and presenting a bit on results on the microstructure, just to show that how the laser is welding the aluminium, and some results on the tensile and the spring back evaluation. So to briefly on the tailor welded blanks, the concept is making sheet metals from combining different portions of metals together, make a tailored blanks, so that it can be the difference can be in terms of material, or it can be in differences in the thickness, or it can be differences in properties. Some sheet metal, maybe they have coating, or maybe they have some treatment, so that make it different. So combining them, even though, let's say for example, they are from the same alloy, but because of the different treatment, so it becomes different responses. And then what we do is that the material will be joined. Usually for welded blanks, it is joined in a butt weld configuration, and to make larger tailored blanks, and which is then subsequently it will be processed as for stamp parts or drawn components. And its application, it is being used for the structure of vehicle. For example, this is a side structure. So you can see that these components, they are having a different thicknesses, and even here they have a different material, different material. So that we are placing the strength and the where it is needed, the strength where it is needed, and it is being used for steel-based sheet metals since 1980s. It is being used in mostly in high-end vehicle because this is new technology, but it's being used for mass-produced cars nowadays. So for the door component, you can see there's a line here. So this is one part will be different, and another part with different material. Okay, and this is a indication where the tailor welded components can be used in the vehicle. So mostly on the sheet metal components, sheet metal components such as the door sides and the body shell, the bonnet, and so on. And they are having two types of components. Either it is welded as a butt weld, tailor welded blank, or it can be made as patch blank, overlapping. So for previously for steel tailor welded blank, the weight is being reduced from the normal single sheet metal. But if you the motivation is that if you convert it to aluminium, it will be, because aluminium is just 1/3 of the weight, the density of steel. So in a way, it is being lighter. And then if you start incorporating aluminium into tailor welded blank components, then the reduction, there is more potential reduction of weight. A little bit on laser. So laser welding, it is not actually a very new technology, but the recent development in fiber, previously it was using carbon dioxide lasers, which have a higher wavelength, which means that the heat source is heat input is big. But the recent development in fiber lasers meaning that the wavelength is smaller, and it is more efficient, and it is more the beam is of higher quality. So there's a new applications or new interest in fiber lasers. And fiber lasers, as you can as from recent development, there are many types. The high-powered lasers and the medium-powered and the low-power lasers. And usually the low-power lasers are being used for very small application, thin applications for micro applications. And if the ones that we are having in the lab, a very simple low-power laser, which is in a way it doesn't require that much power or the in terms of any uses. So it can be installed easily. And in terms of laser welding, there are three modes of welding. It's called conduction welding, transition, and for higher power, you go for penetration and keyhole welding. Okay. So coming back to my research, as I said, the laser joint tailor welded is already in commercial use, but the laser joining of aluminum sheet is challenging because it is not so easy to weld aluminum because of the reflectivity of the material. And we have proposed that low power lasers, it is not being well documented. Not many research. There's a few research going on low power lasers, but not much on actual welding of metals. And so the research proposal is on the investigation on the welding and subsequently formability of two dissimilar alloy. In this case, we are choosing the 5 series and the 6 series aluminum alloys, and see in terms of their mechanical properties and the formability properties. As Dr. Baha mentioned, that the formability studies are not being explored in detail at the moment. So this is something that we are currently pursuing. So this is the laser that we have used. It's a Rofin Star Fiber 300 with a maximum power of 314 watt, and it has an 1070 nanometer emitting wavelength. So continuous mode, meaning that it is very very flexible. It can do pulses, it can do continuous, but in our case, because of the welding configuration, so we are selecting continuous mode of welding. So what we have here is the lens system. So the lens will position the beam, the laser beam. The scanning is called a scanning lens. So we will scan the length of the weld. So in our case, because of we had a previous some studies before, so we are proposing we call it a double-sided. Because of the low power, then we found out that the penetration depth, it cannot achieve what we desire. So we proposed that the weld can be done in 2 passes, meaning that you will do 1 pass, and then the specimen is turned over, and we do a second pass using the same parameters on the other side of the specimen. And the material section, this is from the handbook, and then actually we did actually do EDS to actually see what are the components in the materials. And just to show you, this is the configuration of the plates that we have used. One plate is 63.1. It's another plate, and this is the pilot light. So this is where we are welding. And then this is we are arranging here. And then when we actually welding it, it is being weld. This is very fast weld. It takes around less than 10 seconds to do the 10 mm well. So for our preliminary test, what we did was we weld 6061 and 5052, and we arrange it into a Taguchi experiment just to see what are the influencing factors. So in this case, we just evaluate the laser powers and the welding speed, and so on. So on this for this test, we have tested 3 groups. So the same alloy but different thicknesses, different alloys with the same thickness, and a different alloy and different thicknesses. And what we have found is the output of the cross-sectional profile. So you can see that the weld is being, to the naked eye, it is a successful weld, but we need to evaluate later on. I'm not sure, I'm not showing here, but we did a microstructure and analysis to see how the beam is actually interacting with the material. Okay, so this is dissimilar thicknesses, and this is for the similar thickness. In terms of tensile strength, overall, in general, for all sample, it was less than the base material. The strength, tensile strength is less than the base material, but for some of the sample, it is approaching the tensile strength of the base material. As you can see, for set 9, different thicknesses and different alloys, it is approaching the base material thickness strength. I'm not sure you can see clearly here, but you can see the height, the penetration depth of the laser. It's around 800 micron. So one side in this side and one side in this side. So we can see that in some cases that because of the nature of the beam, very fine beam, so any minor misalignment, you can actually see it is not being. It is very difficult to have it aligned for double-sided unless you have some automated system. Okay, for the same alloy but different thicknesses, and this is much more clear for the same thickness for 2 mm. You can see that for 2 mm it cannot be done because the penetration depth is only 700. So you have some areas which is not being welded. So this is one of the reasons why the samples are having less tensile strength, because only portion of the sample is being welded. And this is a good example showing that the samples the weld are overlapping on both sides. So for 1 mm and 1 mm of different materials, you can see that the weld is being made without much difficulties, with this no misalignment and so on. And this is another one on the dissimilar thicknesses. And even here you can see that there are no gaps. There are no lines of connection. So showing that the weld is overlapping. So from a slide Taguchi, we can see that most of the significant is on the laser. I think it's on laser speed, laser power, and laser power is more significant than the laser speed. So it tends to have in terms of ranking, laser power is more ranked. It's more, have a higher influence on the tensile strength. Okay, this is for overall for all the samples, 3 groups. So for the tensile, what we have observed it is that it achieves 86 and nearing to the tensile strength of the lower specimen of the lower parent material or lower strength parent material, and the laser power was shown to be having the biggest influence on the load, unless one of the segment has a thickness of 2 mm. I think the 2 mm was because of the the well was not successfully made. And as for number 3, we have mentioned that partial penetration was observed for thick specimen, and for smaller specimen, 1 mm thicknesses, we can see that there's an overlapping of the well bit, which is desirable, and unfortunately, porosities are observed, and this thing can influence the mechanical properties. For welding of aluminium, the porosities, even in welding of using other technologies, porosity is something that which cannot be avoided, but we try to minimize for porosities. But this will be another areas that we can look into. So porosities usually it is caused by entrapment during the welding. There's a entrapment of gases during solidification. A little bit on the spring back studies that we did later on, and spring back is important because the understanding of spring back is important because once we have form or create the specimen, the component that we want, we need to take into account spring back. Spring back is that once because of the elastic recovery, you bend it and it will tend to return to its original shape. So in most cases, for sheet metal welding, spring back is something that we need to take into account. Either we can modify the die to take into account the spring back, or we can do some other processes lah. So the final shape it is deviation from the shape that from the working shape of the die. Okay, so why it is important is because large structure is really made up of sub-assemblies. So for example, you make one component of the car, you stamp it, we need to assemble it. So if it doesn't follow the shape that we want, then the assembly will become very difficult. Okay, so these things that we need to understand. So things that we cannot same like porosity, things that we cannot avoid, but we need to understand. Okay, there are some many studies that was done on methods of evaluation, either by V-bending, 3-point bending test, or customized bending devices. So in our studies, we are focusing on the V-bending because the V-bending is quite straightforward. So for the sample that we have prepared, coupons from the same welding plate. So coupon of 20 mm by 100 mm, and then we have selected several two groups for similar alloy and dissimilar thickness, and dissimilar alloy and similar thickness. So we have focused on the 1.5 mm and 1.0 mm only, because from the previous one we have seen that the 2 mm is quite difficult to weld, and the results are not so good lah. So we are focusing on our second section on only the 1.5 mm to 1.0 mm joint. And then these are the welding speeds that we use, the same parameters that we use. And then we have designed this jig, V-bending testing jig, and which is mounted on the instrument machine. And then we what we did is that we move the punch, and so that the coupon will feel will bend by the punch, and it is kept. You punch it until it reach the bottom, and then it is released, and then the coupon will the specimen will tend to spring back. So the angle is because it's 90 degrees angle, so the difference in the angle uh, indicates the spring back angle after unloading. So we use a profile projector to accurately measure the spring back from the specimen after being punched. And to compare, we tested it on the parent materials, so we can know even the parent material that we have spring back, so we know what are the range of spring back for the aluminium 6061 and the 5052. So from this evaluation, you can see that the spring back for 6061 is higher than the 5 series in our case. For all things, 1.0, 1.5, and 2 mm. So we have some 2 mm also, just for comparison. And you can see after we did on the specimens, these are the results that we got from group A. Group A, the blue ones, and group B is the yellow one. So it is the result is in between. It is not reaching the 6061, but at the same time, it is not at the bottom. So it is in between the parents material. So what we have observed is that the spring back for tailor-welded specimen has a better performance as compared to 6061, but it is inferior to 5052. And for particular laser power, increasing the laser power welding speed would increase the spring back angle for the joint. For particular laser power, what particular power? So for this one, it tends to be higher. For particular laser power, tends to be higher for the laser welding speed, increasing laser speed. Okay, that is all for the presentation on my part. I hope it can be beneficial and as an introduction to the fiber welding for dissimilar aluminum alloys. So thank you very much.
Okay, terima kasih. Thank you, Mr. Fadzil, for his interesting presentation. All right, without further delay, I would like to call Mr. Muhammad Zulkhairi Rizlan to present his work. You can start when you are ready.
Okay. Assalamualaikum.
Assalamualaikum.
Alright, Assalamualaikum and good evening everyone. My name is Zulkhairi and I'm about to share about my research here, which is for mobility study of aluminium and steel friction stir welded blanks. So in terms of application, the tailor welded blank of aluminium and steel is used in less critical section of parts where it is necessary to use high strength steel but require lightweight components. For example, in automotive industry, high strength steel and lightweight aluminum alloys were applied to enhance performance, reduce weight, and with reduced weight, you get more fuel efficiency, and this is beneficial to comply with the fuel economy standards. Some of the industrial applications that has been utilized tailor-welded blanks can be seen in the Honda Accord 2013 models, where they use friction stir welding, cast aluminium and stem steel in the engine parts and C-frames. Another one is the Mazda MX-5, where they use friction stir spot welding, aluminum steel and aluminum alloy and steel on the trunk lid parts. For shipbuilding, use of aluminum and steel joint can eliminate problems from such as presence of crevice and galvanic potential difference, which will result in corrosions when using mechanical joining methods such as bolting or riveting. So the challenge in the tailor bank of aluminum and steel is the difficult to use to join when using conventional friction welding due to the huge difference in thermomechanical properties. And welding with high heat input can cause severe grain growth, which will result in problems such as composition segregation, distortion, and cracks. So this is where friction stir welding came in handy. So because it allows the similar materials to be joined by pressure and plastic deformations under the melting point, as can be seen by the animation here. Friction stir welding works by using a tool, a rotating tool, which is rotated and plunged into the interface of two workpiece. The tool is then moved through the interface of the workpiece, and the frictional heat cause the material to heat and soften. The rotating tool then mechanically mix the softened material to produce a solid state bond. Basically, the parameters in friction stir welding should generate enough heat to properly plasticize the material and ensure a proper material mixing. Since improper process parameter can result in excessive or insufficient heat input, which will cause a low quality weld joint or formation of defects. There are many parameters involved in friction stir welding, but based from previous works as well as mine, the two most influential parameters are rotation speed and welding speed. So these two parameters are the most responsible for heat input variation in friction stir welding. For example, if the rotation speed is high, then the heat input will be high as well. And contrary to rotation speed, for welding speed, if the welding speed is high, the heat input will be lower. For formability is the ability of metal workpiece to undergo plastic deformation without damage. And for post-forming evaluation, focus on the blank condition after forming, which indicates limit to shaping or forming ability, and it is crucial in product design. There are two post-forming evaluation of a joint can be done using bending and formability test. Bending test determine the material's ductility, bend strength, fracture strength, and resistance to fracture, while formability test evaluate the material's ability to be formed. Bending tests such as V-bending, which I use in my research, is used to obtain the spring back value. Spring back occurs when the material tries to return to its original shape after being bent because of its elastic recovery. For formability test, in my research, I use limit dome height test. Specimen in limit dome height test is known to experience deformation. Sorry. to experience deformation in biaxial stretch mode, which is generally observed in sheet metal forming. And limit dome height test simulates the common failure strains in sheet metal forming process. From the animation in LDH, strain concentration will develop in the wear region or the center of the punch as the punch continuously move. And the dome height at maximum is used as a measure of its stretchability. So from the limit dome height test, forming limit curve can be plotted by using the strains. In limit dome height, the material can sustain strains underneath forming limit curve without failure due to necking or fracturing. Forming limit curve shows the transition from safe material behavior to material failure, and it is used to optimize sheet metal forming and also as a failure criterion for formability prediction. That's all for me. Thank you.
Okay. Thank you, Mr. Zulkhairi, for this presentation. As I mentioned before, our main focus in the research, especially at the metal forming lab, we try to explore on the application of the tele-welded blank, especially during the forming process. So we can see how what is the behavior of the material after being welded, either using laser or using fusion stir. Okay, I would like to open to the floor if there is any question regarding both presenters, what we have presented, they have presented just now. Yeah, anybody can want to ask, please, or you can type in the chat box so that I can read for you.
Assalamualaikum.
Salam.
For Mr. Zulkhairi, my
Hi.
question is, what is the optimum parameter for your study to weld the aluminium and steel?
In my work, I test 3 parameters, which is rotation speed, welding speed, and plunge depth, which is the amount of shoulder that penetrate into the workpiece. And by using tensile test as a measure of joint strength, I managed to get optimal parameters as follows. Rotation speed 865 RPM, welding speed 90 mm per minute, and plunge depth 0.275 millimeter. Thank you.
Okay, thank you, Mr. Ahmed, for the question. Mr. Zulkhairi still in his experimental stage where still explore on the experiment setup and just begin to what we call as harvest his result for the last few months. So still under the validation stage. Okay, my question to Mr. Zulkhairi as well. Okay, did you expect any, for example, aluminum that you use is 6061, right?
Yes.
And steel, the aluminum is treatable. You can heat treat it to improve the properties. While for the steel, most likely not lah. So if you conduct the heat treatment process, what do you expect from the result? Is there any effects to the formability, even for the rebending behavior of the blank?
For well, for the tailor welded blank of aluminium and steel, obviously, when I did a heat treatment, there will be effect on the aluminium side, even though the steel will not have any effect at all. So, if let's say I did the heat treatment and did, for example, bending process, uh, it will affect the resultant spring back value, although it may not be as high as, let's say, I use both material, heat treatable material for both part, but still it will influence the uh, final result.
Okay, thank you. Anybody? Want to ask any question to our presenter? We have
Mr. Zul,
here.
I would like to ask on the specimen thickness. Did you experience any difficulties in joining a thin? It's quite thin, right? 0.
Yeah. For specimen, I use 1.5 mm.
Is there any difficulties in joining? Because we did some very thin materials and it's quite difficult to join, especially.
Yeah, I think the problem when joining thin specimen using friction stir welding is there's a warpage that tends to happen if you didn't really clamp it good enough. So in make sure compared to thicker materials, the
Yeah.
warpage might not happen at all. But for thin material like 1.5 mm, so the warpage might happen and this will affect the final product because your final blank will not be as straight as you like them to be.
Mhm.
That's the main difficulty that I encounter from my work.
So the solution was in proper clamping lah.
Yes.
Okay. Right.
Okay, any other question from the floor, from the audience?
Okay, Assalamualaikum for both presenter. My question is actually specific to Cik Muhammad Rizal lah. Fadzil, sorry. Cik Muhammad Fadzil. I was the line was not clear here just now, so I couldn't catch you whether the laser, the fiber laser you use is how many watt?
310.
That one is the maximum lah.
Yeah, the maximum.
Maximum setting lah.
Maximum. So it was under. It's a low powered lah. It's considered low powered. Kalau go from physics side, it's a high powered, but from manufacturing side, it's a low powered laser.
Yes, correct. It's low power. Does it have an option to do pulse?
Yes. It has option to pulse. And from our reading, it is much better to do pulse or wave
Yes.
shaping. But for the duration of this study, we only managed to do the continuous wave. But subsequently, after we did some of our experiment, actually, if we do a pulse mode, or you call it the wave shape mode, because a laser is quite flexible, then I think it will be a better result, better quality lah. But for the purpose of our studies, we are only limited to continuous wave.
So you're focusing on continuous wave only lah.
Yeah, on the side. But because we have done the experiment, and we see that the machine, there are many options that you can do actually, because it is not because they are positioning the laser by scanning. So actually there are some configuration that, for example, they can do wobble, it's called wobble laser. So that it doesn't really matter on the it will cover a wider area lah kan. So those are things I think we can do later on lah.
Okay. Because I was wondering, because from your result, seeing that you are not able to weld more than 1.5 around that, right?
Yeah.
So I think since you have that option of pulse, because when you have pulse, the average peak power will actually be more than 300 above. So then you actually
I
pick the material.
Yeah, peak it can go higher. It can for it for 2, I think you no problem if you pulse. But from the limitation that we have set up from the earlier design of experiment, so we just focus on the continuous wave. So those are the limitations. And actually, in terms of applications, for example, if you are using for sheet, metal sheet, so 1.5, 1.0, there are some applications that you use. It doesn't really require to go higher than 2, for example.
Okay, right. Okay, thank you very much. Good.
Okay, Assalamualaikum.
Assalamualaikum.
Oh, boleh. Okay, I have 2 questions. One for Mr. Fadzil and one for Mr. Zul. The first one is Mr. Zulkhairi. Can you share what is the factors that influence the spring bar result on your research? And for Mr. Fadzil, actually, as we know, the develop or produce the tabular blank, we use conventionally use like friction stir welding. We have a rotating tool to stir the balls of materials. So can you explain how the function laser it works? It means if we use a rotating tool, they have a rotating to stir that material. So is it the laser also have a function or element to stir the balls material, or how? So that's all for me. Thank you.
Zul?
For spin back, I think the main factor is the modulus of elasticity of the materials, because this the resistant to being deformed when stress is applied. So higher modulus of elasticity equals lower spring back. And then another factor that I tested in my work is the material thickness. Higher thickness equals lower spring back. And the punch stroke, which is the how deep the puncture went down when during the bending process. So higher punch stroke result in lower spring back. That's all.
Mr. Zul.
Okay. To answer Mr. Amir's couple of question on the laser. A laser is actually like welding lah. You have the arc welding, kan? So actually the thing will melt the material. So in my case, usually we have a filler material to fill in the gaps, kan? Kalau welding in some of the welding they have a filler material, but in this case it's called an autogeneous welding, whereby they don't use a filler material, and it is melting both sides of the metal, the parent material, and then when it is melted, melt and solidify, so it is being joined. So we did a subsequent study. We can see the the mixings of the material due to the melting of both sections. So we need to make sure that the laser will melt. It has to be exactly melting on both sides. So the purpose that we are not using filler material is that the filler you need to have additional components lah. But in our case, we try to maintain a simple configuration, just two parent materials, and then we apply just the laser. So in actual practices, it is possible, but you need to play around with the parameters lah. But in normal cases, ataupun in normal welding, they usually have some sort of filler materials inside.
Okay, thank you, Mr. Fadzil.
Okay, thank you from Mr. Kamarul for the good question. Okay, if there any question, would like to ask to our presenter. You can ask about the metal forming lab as well if you're interested to know further. Okay, my question to Mr. Fadzil. If I'm not mistaken, you show that you need to weld both sides, right?
Yeah.
In terms of production, how we can optimize so that because if we increase number of welding, means that we will increase the cost. So how we can optimize that? That we can still join material with good strength. At the same time, we can do it at very low cost.
Because I think for this case is a limitations of the power, laser power. I'm suggesting for production, maybe the laser we can use a slightly higher power laser, because in some of the samples that we have recently it is approaching, it can do one pass, but approaching one pass lah, tak lepas lah. It doesn't fall and to for the thickness of the specimen. Another method is that because of the fiber actually you can do split. You can split it, the beam to split, but then then there's you need to have a different type of configuration lah, meaning that in one pass you can do both sides at the same time. But that one involve some sort of configuration to the laser head lah. So that will increase the it may require some special design of the laser head lah. So on one pass you can do on both sides, of the material. But for our case that we can do, so only can do on one side. Even if you want to turn, industrially it's quite difficult lah, because if you start turning the metal, then there's issues of alignment. Another option is that is to use a robotic arm that you can have it in one go and then move it to the bottom and do another one. But then that's involving additional design of machines.
All right. Thank you again to the both presenters.
Excuse me, sorry, Mr. Chairman.
Yeah.
Can I further suggest to
Yeah.
apa ni? Fadzil, because
Mhm.
bought that two-sided welding kan.
Hmm.
Why not you try to do pulse
Yeah,
for the
pulse can be
same
done.
thing,
Pulse can be done. Yeah.
pulse, so maybe it can penetrate from top to bottom. Maybe you
Mhm.
can try. It's an option to try. So
Yeah, yeah, that's
you
an
don't
option.
need
That's an
to
option.
overturn the welding plate, right?
Mhm.
Maybe
Yeah,
one
yeah,
of
good
your
idea.
research area lah
Mhm.
to look into, right? How to see how the penetration is.
Yeah, yeah.
Because uh, with pulse laser, when you reduce the frequency, it is actually like continuous laser lah. It reduce the frequency of the pulse, so it will be from one pulse to another pulse in very short period. So practically,
Mhm.
a continuous welding lah. It's very fast lah. I don't know the setting of the fiber laser, so you have to actually explore on that area lah.
Okay, thank you very much, sir.
Thanks. Thank you. Assalamualaikum.
Okay, thank you, Mr. Muzani again. All right. If no more questions, I would like to thank you all the audience, especially the two presenters today. Just to alert you about another webinar that we are going to organize soon, inshallah in April, something like that. We are going to share another topics on teller welded blank as well, but more to the applications. I didn't prepare the poster yet. However, I can give a clue on the title. One is about the performance of teller welded blank during the single point incremental forming. Most likely will be presented by Mr. Kamarul, one of my PhD students. Another one will be the effect of joint configuration of a teller welded blank on crash worthiness. Also will be presented by one of my PhD student, Mr. Ameh Shraki. Soon, inshallah, we will keep updating the program event organized by the Metal Forming Lab, USM. All right. Okay, other CPD point. Yes, you can try to fill the form and submit to the USM. I'm not really sure whether they they will give you the point. Inshallah, I think it is supposed to give lah, because it is also a professional development as well. All right. Again, I would like to thank the participants or the attendee or the audience, and as well as the presenter again. See you in the next webinar from us. Okay, with that, I think I would like to say that. See you again, and Assalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum.
Assalamualaikum.
Thank you, bro.